I'm Robert Hawkins, a postdoc at Princeton University, and this is joint work with Noah Goodman, Adele Goldberg, and Tom Griffiths. One of the most useful things about language is that we can use it to understand people we've never met before. I can walk into any coffee shop in America, ask a complete stranger for an espresso, and expect to get roughly the same drink whenever I say the same word. This ability to effortlessly generalize to new social partners and contexts is a fundamental property of what we call social conventions, and specifically linguistic conventions about what words mean. But what cognitive mechanisms allow these conventions to form in the first place? How do we form beliefs about entire communities when we only have direct experience talking with a relatively small number of individuals? I'll argue that the first step is to recast this problem of convention formation as fundamentally a cognitive problem of induction or generalization. How do we make this inductive leap from partners to populations? Well, to get some intuition, try to put yourself in the shoes of a new graduate student joining a lab. They might come away from their first meeting with their advisor with a bunch of new words. How do they know whether this is just the idiosyncratic way their advisor talks about things, or whether the whole lab talks this way too? If other people in the lab seem to know what this particular term X means, you can be pretty sure that it's a convention, and you might feel more comfortable bringing it up with someone new. So this is the basic intuition about the phenomenon we're interested in. But what cognitive mechanisms explain this ability to generalize across partners? One simple solution, going back to Luke Steele's and others in the mid-90s, is that you can basically ignore social identity and use the same model for everybody you talk to. So suppose that you have a big community represented as a social network where each node is an individual and each edge means these individuals might bump into one another. You can run a simulation where you randomly pair up agents and have them talk about stuff. So suppose that I'm an agent in this network. At the first time step, I might be paired with my neighbor, 32. We talk, and they use the word A to name this object. So I add that to my memory bank. Now I'm paired with a different partner, partner 10, and use my current memory bank to interact with them in my best guess about what will be meaningful. But maybe they say B. So I add that to my memory bank too, and I carry on doing this with many different partners, updating my memory bank along the way. We call these complete pooling models because they pool together all of the data from different partners without exactly remembering which partner said what or whether a particular partner has been encountered before. Of course, this memory bank with a sort of majority rule, production rule, is kind of a cartoon from early papers, and more recent work has explored much more sophisticated models. For example, recent work in the emerging communication literature often uses sophisticated end-to-end reinforcement learning to modify a very complex utterance production policy. But all of these models we still call complete pooling because they don't differentiate between different partners or contexts. They update a monolithic representation of language. A problem with this, although it can efficiently lead to consensus in a large population, anonymous matching may be realistic for some conventions, like coordinating with other drivers in which side of the road kind of convention, but most of the time our interactions aren't one-shot interactions with anonymous strangers, especially in language. It looks more like this, where we talk to a particular partner for a while, where this entire red block is talking to partner 32, and then we might have another block of talking to 10 later. And we know from classic work by Dina Wilkes-Gibbs and Herb Clark that people actually care about these partner boundaries a lot. So complete pooling predicts that when we switch partners, we'll readily extend the same conventions. So that's this dotted line. But that's not what happens. People know that the common ground they built with one partner isn't necessarily shared with another. Now, one way you might think to patch up this model with respect to social identity is to add a kind of um, index for your memory of a particular partner. So you know you're interacting with partner 32, you activate some partner 32 model, and so on with other partners. And the important part of this kind of model, which we'll call a no pooling model, is that you maintain separate models for each partner. So this solves the partner specificity problem. An agent with a no pooling rule isn't going to try to extend a ad hoc convention that they formed over an extended interaction with one partner to the next. But this has a really serious problem in that it's unable to generalize. When you encounter a new partner, you just have to initialize a new model. So a convention can never get off the ground. So in our work, we proposed a hierarchical partial pooling model that overcomes the limitations of both of these complete pooling and no pooling classes of models. This model integrates three core cognitive mechanisms. First, we need to formalize the idea that people account for the overall variability of meanings in the population with some uncertainty over what a particular partner thinks our words will mean. In other words, we have to bring some kind of background expectations to an interaction. Second, after we've gotten some evidence from a particular partner, how that person is using language, we need a mechanism allowing us to quickly update our expectations in a partner-specific way. And finally, we need some mechanism specifying how the evidence we've gotten from one partner is expected to generalize to others. So we need a theory of generalization. And a hierarchical probabilistic model satisfies all of these desiderata by sharing statistical strength across partners that are expected to be drawn from the same overall distribution. It also has a nice interpretation as a model of convention formation as meta-learning, trying to solve the communication problem with mini tasks across many different partners. So that's the math, but what does this actually look like in practice? Well, we can draw a useful schematic from the literature on meta-learning. So we can think of this big theta that is our shared top-level community beliefs as an initialization point in the space of possible systems of meaning. And we can think of the partners being used by our new partner, K, as living somewhere else in this space. And as we interact with K and observe how they use language, as we produce and listen to them, we can use this likelihood function given in green to move closer to where we're inferring their particular model is in this space. So you can think of each time step as kind of a jump in this space of beliefs. Finally, once we're done interacting with a partner, we can think of the prior that we bring into this interaction as a kind of regularization mechanism, making sure we don't move too far away from this big theta without sufficient partner-specific evidence. And finally, this hierarchical inference mechanism allows us to systematically adjust our initial state closer to that partner after an extended interaction. So over time, as we interact with more partners, you can kind of think of this big theta as finding an initialization that allows us to quickly adapt to each new partner we might encounter. So the meta-learning part is this idea that all of these partners share something, which is the place we start when we interact with them. And we're trying to figure out where in that space is the best overall reflection of the distribution of different partners. So you can find more details about exactly how we've implemented this model in the paper. But to evaluate this model, we wanted to design a networked communication experiment that we could run with both simulated agents implementing these different models and human participants. So we used a communication game, a reference game, taken from early work by Herb Clark. So in this game, a speaker and a listener agent are paired in a virtual environment, and they're both shown a grid of these tangram objects. On each trial, The speaker is cued with one of these tangram objects as the target, and their job on that trial is to produce a referring expression in the chat box that will allow the listener to pick that target out of their own shuffled context. So after the listener makes a selection, both participants receive feedback. So the listener finds out what the true target was, and the speaker finds out what the listener selected, and then they move on to the next trial. Importantly, this goes on long enough that each target appears multiple times. So we can observe how the language that speakers use to refer to an object changes over the course of the interaction history. So we made small networks of 4 participants and created a blocked design where the first 16 trials were with one partner. So each target in context was seen 4 times. There were 4 targets. And then they swapped partners. So then they played the same game for another 16 trials with that second partner, and then they swapped partners again to play the same trials with the third partner. So we were particularly interested not just in the utterances within interaction with a particular partner, but what happened at these partner boundaries. So what does our model predict will happen in this game? The first thing we're interested in is the listener's behavior. How does a listener generalize from partner to partner? So we can look at the accuracy of the model in picking the correct target over time. So in our simulations with a complete pooling model, the signature phenomenon is that there's no change at partner boundaries. They just barrel forward using a monolithic representation of every partner, ignoring the fact that 2 identities might have different language models. A no pooling model, by contrast, has exactly the opposite signature. So it completely reverts to baseline with each new partner. And a partial pooling model, as described earlier, splits this difference. So there's a big gap at each partner boundary where we regularize back. We don't want to extend all of the common ground that we formed with one partner to the next. But over time, our generic community level beliefs become strong enough that we're more and more willing to extend the same common ground to partners that we haven't seen before from our community. So what we find is a pattern of empirical data supporting this partial pooling model. So we find a significant drop in accuracy at partner boundaries, as well as an overall trend increasing accuracy on the first round of interaction with a new partner. Our second metric that we wanted to look at was speaker number of words. So our complete pooling model does form pacts and get more converges on more efficient referring expressions over time, but again, no difference in partner boundaries. Our no pooling model completely reverts at partial boundaries. And finally, our partial pooling model quickly adapts to each partner, but also becomes more efficient with new partners and more willing to extend these conventions. And again, we find that the empirical data support our partial pooling model. Finally, we were interested in the overall network convergence. So we measured the alignment between partners that are currently adapting, this is within dyad, and partners that aren't currently adapting. So they're in different interactions within the same network. And we see that the partial pooling model is the only model that predicts consistently high within partner alignment while increasing across dyad alignment. And again, that's exactly the pattern we find in our empirical data. To wrap up, our work has aimed to articulate a cognitive model of generalization that reconciles partner-specific common ground with the emergence of population-level conventions. Unlike complete pooling models, which have no mechanism for representing partner specificity, a meta-learning account successfully captures the empirical pattern of generalization and provides initial evidence that partner-specific common ground is not only compatible with emergent convention formation, it may in fact facilitate it. Thanks.